Okay, thank you, everyone, and welcome. My name is Joshua Ho. I am from the University of Hong Kong. In fact, today I'm here presenting on behalf of my student, Irfan, who is unfortunately not able to come due to some visa issues. But I'm very delighted to be here to share our work together. Let me explain the problem, why we want to do what we do. We are interested in viruses, in particular, all sorts of viruses. There are viruses that you commonly know, including the viruses that cause human diseases like SARS-CoV-2, like influenza. But of course, there are huge amount of other viruses that are actually occupying inside your body that are not pathogenic to you, including a lot of bacterial phages. Right? In your human gut, there is actually a huge amount of bacteriophages that are living in you, and being able to quantify them rapidly is actually really important to understand the biology. And of course, there are a lot of environmental viral sequences that are around as well. So it's very important to be able to identify and quantify what they are. So there are a large number of families of family members in viruses. So we want to have a good way of identifying them. So one very powerful way to do it is shotgun metagenomics. Sometimes you can couple that with experimental procedure to enrich for viral elements, or sometimes you just do bulk unselected metagenomics. So these are all possible. And then at the end of the day, you just do extraction of DNA, or in some cases, extraction of RNA, do fragmentation, and then do sequencing. That is the experimental component. The difficult part is actually at the end, when you do the bioinformatics analysis, when you align the short read into with some kind of reference databases, or do contig assembly, assembling contigs, identifying the identity of individual viruses. That is actually really, really not easy. So I've been working in this area for the last 5 years. I've been working with a lot of clinicians who have been collecting a lot of human stool samples for various cohort studies. So we have been building some tools using best practice in the literature. We've been building some pipeline together. So let's do that. Okay, so we have collected a lot of this. We have some basic pipeline. I asked my student, Irfan, to do it. That's not him. By the way. So we just got lots of data set. He took our big pipeline. I've been trying to run it. He's been very excited. There is putting all this pipeline together, running it, submitting the job, expecting some results to come soon, but it does not. He kept waiting, and questioning whether there's even trustworthy results at the end. And after 2 weeks, the program crashed. So basically using up a huge amount of memory, and there's really minimal data that he can get out of that. Then that's actually where the bioinformatics side of the story began. He actually looked into every single step of the pipeline. There are many programs that are involved in this pipeline. So he did some kind of forensic investigation to work out where it took most of the memory, where it took most of the time, and what are the bottlenecks. So basically, he, being a very meticulous programmer, went into the code and looked at that. So this is a huge convoluted pipeline. Actually start from the left-hand side, or on your side, right? Start from some kind of FASTQ file. It can be downloaded from SRA or from our own internal list. Do some basic processing, do assembly, and this is standard assembly. And then going to the viral quantification. This is really one of the heart of what we do in terms of viral annotation. In particular, the use of GenomeAD, which is a relatively newly developed tool. We decided to use MegaBlast because it is a lot faster than CityHit. And this is actually quite important. We actually optimize a very critical step called CheckV. So CheckV is a tool. So if you do metagenomics, you would have used this tool. It's a very useful tool, but it is actually relatively slow, particularly if you deal with very large file. And we actually did quite a few things. That the trick is actually divide and conquer. So there are some steps that actually take a long time, particularly big memory use. We analyze why it happened, and then we did something basically using a divide and conquer approach to really massively speed up that processing, make it much more feasible to do. and then to generate the output. We also do taxonomical identification, and of course, we actually also look at the bacterial component as well. So we do bacterial quantification. So in short, we now have an end-to-end pipeline. We put together a snake-make containerized environment so that instead of having a script that put together 10 different tools, we have a very nicely, easily installable container environment to run the system. Again, there are individual components, including CheckV, that we have significantly improved the overall performance, including both speed and memory usage, which is very critical. Our tool is called vOMIX-MEGA, and hopefully that tells you that it is very fast. Okay, and this is the demonstration that this is very fast. We have been doing simulation of data of various sizes in terms of scaling, in terms of number of contigs. So the left is 10 contigs and the other is, sorry, you can't see this. Okay, larger number of contigs. And here is how does it scale in terms of number of CPU. So basically, and this is in log scale. The y-axis here is in log scale in terms of the wall time, clock time, right? So this is actually really a massive amount of speed up compared to other commonly widely used programs to do similar things. So instead of, in fact, we cut off here, as in after this time, we just didn't run the program. So there's actually no outcome at this point for some of the tools. So we are, magnitudes of runtime faster compared to other things. And of course, it also scales well with providing more CPU. So it's a very scalable program. So here is the gist of how we improve the performance. We particularly use different packages, and particularly we use PyHammer versus Hammer. And also we also optimize the use of this PyHammer in CheckV in order to really get the speed up that we want. So we know it is faster. Is it more reliable, or at least as reliable? So we did some evaluation. One is using a mock data set. So we generated synthetic data, so simulation data, as well as we use a real experimental data. And this is a data set where people experimentally separated a viral component from the non-viral component based on size. So this is an experimental separation, not a computational one. And then, so therefore, we can kind of use this as a ground truth data set for the sake of our performance evaluation. So based on both experimental and mock data set, comparing our two, vOMIX-MEGA versus others, actually we have two versions of vOMIX-MEGA. One is the recommended version. The other actually allows you to use, actually in this step, in the viral contig identification, there is an option of just using GenoMed and the other option of using GenoMed plus the other somewhat commonly used tool for viral identification and take consensus. So we allow both of this to occur. So, but what our results indicate that actually just using GenoMed is already, in fact, better, not only speed, but also in terms of overall accuracy, sensitivity, and specificity of detection. So we do well in this regard, and this is true both with both experimental and our mock simulation data. And looking at GenoMed versus other options, GenoMed does perform better. So that's why we just use this as a default recommended version of our pipeline. So again, this is using mock data set. We can calculate this ROC curve, and it performs quite well. Okay, so this is a summary. We hope that this will become a useful tool for anyone who are interested in identifying and quantifying viral sequences from metagenomics data. And we think we have a lot of useful application. As an application of why we want to have a very scalable tool is because we want to do really large scale analysis. So this is a study that's still ongoing. So we are still analyzing that data. But just to show why having scalable algorithm is very useful, this data set of almost 4,000 human gut sample, it took us 2 weeks to analyze, and we estimated that based on the performance of other tools, it would have taken many more months to do the same analysis on the same data set. So this is something that we are really quite excited about. So we're hopefully getting that out soon, and we're expanding. Hopefully the next step is to expand vOMIX-MEGA into not just analyzing DNA viruses, but also on RNA viruses. And last but not least, and importantly, we thank the funding body that supported our work, and I welcome any questions. Thank you.
That's so good. Hello. I was very excited to see other people doing phages here. I was just wondering whether your pipeline includes steps for functional annotation as well, so things like FROCA to annotate the different genes that are present.
I think it has, although I think Irfan is the best person to answer that. I think it is part of it, or have been a plan to include that, but I can get back to you.
Yeah.
Thank you. Right.
Joshua, thanks. And I just saw that later you will be expanding it to also applicable to long reads, right? So what do you foresee would be the problems when you expand your tool to long reads? Because, the analysis, and especially the two sets that can be used for long read analysis, so different from short reads.
Yeah, I think this is a very much unexplored area. So obviously, very would love to work with you on some of this topic. So all the tests are done on primarily Illumina short read sequencing data. So I don't know the answer to that question, but we would love to explore that.
Cool.
Yes.